Okay. So inverse trig functions, trig functions are sort of challenging. And then of course, inverse trig functions feel even more challenging. You will see sometimes inverse trig functions written like this. This inverse trig, this -1. I don't really like that notation myself because we often put an exponent in that place, right? Like when we're doing, like for instance, if I write this, sine squared of x, that really just means sine of x squared, right? These are the same things. But this -1 doesn't mean an exponent. This is not sine of x to the -1. And that's why I think it's actually not very good notation, because it's like, well, sometimes it's an exponent, but here it's actually not an exponent. And so I prefer to use arcsine and arc as representing the inverse trig functions. And I think the book kind of bounces back and forth between those. So just be aware of that issue. Like I said, trig functions are tricky enough. Adding the inverse trig function feels really complicated. I don't have a solid, even myself is like, I feel shakier with inverse trig functions. Like if you ask me to evaluate this at an x, I'm like, I don't know directly. But of course, the advantage of knowing trig functions is that an inverse function and an original function, you can switch the inputs and you get the kind of original relationship, right? So if y is arcsine of x, then x is the sine of y. And of course, this I'm much happier with, because even though it's an implicit function, it is at least working with sine that I'm happier with. So I think what you were getting at is like, well, okay, if I want to find the derivative, and I don't know what the derivative is, like when I'm starting out, I don't know what this new function is. I'm going to try and rewrite that new function in terms of a function I already know, but this is an implicit function. So when I take its derivative, the derivative of x is 1. The derivative of sine of y is cosine of y times y prime. That's the chain rule for implicit differentiation. And so then I can find y prime. And then I don't, I started off with a function that was just y equals a function of x. So it seems weird that my derivative is now in terms of y. Well, at least it's weird to me. I don't love that. I feel like if the function started out with x, then my derivative should be just in terms of x. And I can do that. I just have to do a little bit of work to figure that out. If the sine of y is x, let's just call this angle y. So if the sine of y is x, sine is opposite over hypotenuse. So let's call that x and that 1. Right? That's if the sine of y is x, then that ratio has to be x. And so the easiest way is just have it x over 1. And then I can use the Pythagorean theorem to figure out what this length is. 1 squared equals x squared plus my unknown length squared. So that ends up being 1 minus x squared and the square root of that. So once I've filled in this triangle, I can then figure out what the cosine of y is. Cosine is adjacent over hypotenuse. So this says y prime is 1 over the square root of 1 minus x squared. And that's our rule then, right? The derivative of sine. Sorry. Lost track, right? I don't want to write it this way. I want to write it this way. Derivative in terms of x of arcsine of x is 1 over the square root of 1 minus x squared. And so I think your question was saying, like, can I just use this formula? Definitely, right? I don't really want to go through these steps each time because I have this formula already. If I fall on the ice and hit my head and can't remember, well, then I could come up with it, right? It's not too hard to come up with, but not really what we want to do. And in fact, we would like to remember, if we're going to remember one version, not just arcsine of x, but the more versatile chain rule version, arcsine of u, which is du over the square root of 1 minus u squared. And that's one, you'd want to write down on your note sheet. There are, of course, 6 inverse trig functions. I will tell you, we don't run across really 3 of them at all. Arc cosecant, arcsecant, and arc cotangent. I don't think they appear again in the book, and if they did, for some reason, you could look them up. So the only ones you need to keep track of are arc cosine, which is conveniently very similar. It's the same, it just has a negative. Like the derivative of all cofunctions, right? They end up with this extra negative there. And then probably the most important of all 3 of these is arctangent. Sorry, I'm very messy here. U du over 1 plus u squared. Yeah, super sloppy, but so those 3 you should write down and be familiar enough to apply those. But I would use them as they're written. I would not try and come up with them unless I was forced to. The real reason of kind of working through this is just so that we don't have this thinking that these formulas are magical, right? Or coming out of thin air. They're not. They're the results of things that we already know. And that's one of the great things about calculus, is that really the whole course is using things we already know. There's very few things that I have to just say, you just have to trust me on this. There's a couple, but not many, even in the whole course. Everything else is like, well, here's the reason why that's true and why that works. You may not always follow the reasoning perfectly or even that much, and that's okay. I think having the sense that it's like, it's there, it's out there, there is a reason why, is really valuable. It's not arbitrary. And this one's actually a nice strategy. We can use that at some other times too, this relationship between a function and its inverse. Okay. I don't know if that answered your question at all, but that was something. Okay, good. That was something I wanted to talk about. So, okay, great. I'm glad we lined up on that one. Okay, so and then once you have these arc and these formulas, you can just fit this into all of your other derivative rules, right? Products and quotients and natural logs and chain rule. It just mixes in, and we just, whenever we see that function, we know how to come up with its derivative. Other questions? Anything else? Okay. Let me just take a second to just review our logarithms. I know we talked about this a little bit on Tuesday, but want to make sure we're very comfortable with this. It does turn out actually that the proof for how logarithms works is really the same strategy as our inverse trig function. So like we often like to do in math, we just mine the same idea over and over again as much as we can. The idea being that when you're starting out, you don't know what the derivative of the natural log of x is. It's a new function. We can't really use our definition of the derivative. I mean, I can write it down, the definition of the derivative. You may also want to write it down because it's going to show up again. Call it y or f, right? It's the natural log of x plus h minus the natural log of x all over h. Right? Remember, that is our definition of the derivative. We've kind of moved away from that definition as we've been learning all these rules and shortcuts. But all those rules and shortcuts really have to come from this core, and the core is the definition, right? So don't forget that, even though it's not really what we'd like to use, right? We want to use the shortcuts. The problem is we don't know how to evaluate this limit. It's got natural logs in it. We haven't done a limit with natural logs. It's very hard to mess with algebraically. So we're kind of stuck by the definition. Our other strategy is to try and rewrite it. You know, sometimes we have a messy function and we can use algebra or something else just to rewrite the function in terms of things we already know. And you kind of can do that in this case, but you have to use this inverse relationship. So I don't know how to change natural log around algebraically, but I do know that if y equals the natural log of x, I can rewrite that as x equals e to the y. Right? That relationship between logarithms and exponents is really important. It's how we solve a lot of equations that involve logs and exponents, and that turns this kind of new function into a version of an older function, right? So just like before, this is an implicit function. It's got x's and y's in it, but I can take the derivative of that function implicitly. Right? Derivative of x is 1, derivative of e to the y times y prime. We do a little bit of algebra there. And then I just have to remember that e to the y is really x. So just like before, y prime, I want to replace that, and I get the derivative as 1 over x. So we think of that again as a fact, and that's the way you should think of it and use it, but it comes from some kind of what we understand with derivatives and implicit differentiation. So remember, if it's a u there, then it's du over u, and that's really the one to remember. You should also note, I won't go through the proof, but it's very similar if you have a logarithm with a different base. So this works for natural logarithms. E is actually defined in calculus as having a kind of this special property where you can define E using a limit and show that this limit is well, it depends what limit you set up, but E is defined, you know, maybe in college algebra, you just saw E as like this random number, right? E was like 2.718, blah, 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 blah. I don't know, maybe you just said, okay, it's a number, wonderful, but it's a powerful number in the same way that pi is a powerful number. All numbers, right, are useful, but these numbers seem to connect to the world that we live in, right? We like circles, and so pi tends to pop up all the time because it's related to a circle, right? And E is, in the same sense, a kind of special number in that it pops up a lot with the way our world works, right? The things we care about in our world. The way things grow and change turns out to relate to this number E. But it can also be defined using limits. And what it does is it makes our derivatives here really easy. That's in some way what E is. It's the number that makes this derivative kind of the simplest. But you can also take derivatives of logarithms that don't have the base E. It turns out it's going to be almost the same, du over u, But because the base is an e, we have this, like, I call it like a correcting factor. We got to multiply by the natural log of the base, a. This formula actually in some ways is maybe the best if you had to know one formula, because it works even if the base is e, right? Because the natural log of e is 1. So this would certainly apply to this situation, but it also applies to all of our other logarithms too, log base 2, log base 7, or anything like that. And then we talked a little bit on Tuesday about this logarithmic differentiation strategy. You can use that for other problems too, but it's typically not very efficient. So sometimes I'll see people do things like, let's say I have sine of x times x cubed plus the square root of x, let's just say. And I'm trying to find its derivative. You technically could use logarithmic differentiation here, right? This is a product. If I took the logarithm of this product, remember the log of a product is the sum of the individual logarithms. And that is sort of easier to take the derivative of, but it also, logarithmic differentiation, remember you have to take the derivative of the left side too, which would then be the natural log of y. So this is not really one that we want to complicate with logarithmic differentiation. We already have a rule for this. It's called the product rule. It's no problem, right? We should really use the product rule to find this derivative. Again, you can get the right answer by using logarithmic differentiation, but it's a little bit like, you know, overpowering the situation, perhaps. But if you have y equals x to the cosine of x, this one, there's no real way around it. This you have to use logarithmic differentiation for. It doesn't, we don't have another rule for this because of its structure, right? Its form. So here we need to use logarithmic differentiation. And then the third case is you might have something like x squared plus 2 times, let's say, make that to the third, times x minus 5 to the 7th, all over the square root of x to the 4th plus x minus 2. So here is one where you can take this one directly, but you should be sort of intimidated or horrified by this one, right? Because you've got a quotient rule and you've got chain rule and you got a product on the top. It's going to be incredibly messy and really hard to keep track of because there are so many products and quotients and powers involved. So this is a situation where you don't have to use logarithmic differentiation, but realistically, that's probably the only way you're going to be successful. Otherwise, you're going to get tangled up. So this would be another case to use logarithmic differentiation where it's got too many things going on. It's worth the extra effort of taking the natural log of both sides because of how much simpler it's going to make the right side. Here, this top one is not, right? Product rule. And that's kind of a general guideline. I'm not going to mark you wrong. If I say take the derivative of the top one and you use logarithmic differentiation and you get the right answer in the end, that's great. Good job. I don't think it's the most efficient way, but that's maybe to you at this particular problem it was, right? So don't worry about that, but I think it's helpful to know, you know, kind of what's necessary and what's an option. Are there questions about any of those? Questions? I definitely want to introduce the related rates. I know some of you have done these or made some progress on these, but some of you have not. Word problems are always a little bit of a nemesis for everyone, unfortunately, because they're kind of great too. And calculus word problems are way better than any of your other word problems because they're actually, you know, a lot of the other problems you could probably solve them if you just sat down and sort of punched through some numbers, right? They're like not very inspiring. But we're going to work through some calculus problems that are like, I don't know how you'd figure that out without calculus, right? They're really answering questions that are not always clear. So I'm going to try and give you some general guidelines for related rates. The challenge with them is that you know, every problem feels different, I think, when you're starting a related rate section. It's like, whoa, this one's about a boat, and this one's about a snowball, and this one's about a big pile of gravel, and like they don't seem like they're connected. But once you see the sort of core of them, you'll realize, well, okay, there are a lot of similarities between all of them. So here I always start. Well, you'll probably, if you watch the lecture, then you'll have already seen my standard examples. I can do a slightly different one. Let's yeah, let's try this one. The sides of a cube are increasing at 2 centimeters per second. All right, so you have this cube and it's expanding. The sides of the cube are increasing at 2 centimeters per second. How fast is the volume increasing when the sides are 4 centimeters, and we'll do kind of a follow-up question, or 10 centimeters. So these kind of two different scenarios. So notice, like, I mean, if you have a small cube and the sides start to grow, if the sides are growing at a fixed rate, the amount of volume that you're adding is really changing. My hands are maybe not the greatest visual example of a cube, but you know, once your cube is pretty big, adding 2 centimeters to all the dimensions adds quite a bit of volume. But when your cube is small, adding 2 centimeters only adds a little bit of volume. So the volume is changing here, but it's related to both the speed at which the sides are changing and also how big the sides are. So this volume is sort of a, you know, it's related or connected to the cube. So that's, you know, something, but it's not totally clear how it's connected. So that's the goal here with related rates, is to figure out how a formula for how these different quantities, and a rate, right, is just the way something's changing. So, and for us, what's really important, maybe I should have mentioned this even beforehand, right, is that the derivative of a quantity gives us the rate of change. So in application problems, rate of change is really the derivative. The derivative is the slope of the tangent line. That's the geometric explanation. But the practical or application definition is a rate of change. It's telling me, is my quantity going up or is it going down, right? If the derivative is positive, it's going up. If the derivative is negative, then it's going down. So it's telling me how fast my quantity is changing. So when I'm working with these related rates ones, I'm really working with the derivative is really what it's asking me about. So, okay, I promised you some steps. Number one, use a picture, if possible. A picture always helps us. Well, I can't say always, right? There's some things that don't make sense to draw, but in many of the related rates questions, a little picture is going to help us organize our information. This one is not super magical because it's just a square, right? It's not telling me too much I can't visualize in my head, but I'm trying really to get kind of everything out of my head and on the paper so that my head is all cleared for actual thinking, right? If you try and hold too much stuff in your head, you can't do the thinking you need to. So think of that with these word problems or application problems. I'm just trying to like get everything down on paper to start with so that I can do the analyzing I need to do. So use a picture, and within that picture, I'm going to define the unknowns. Okay, and I'm going to name them. So what we want to think of here is that the cube is changing, right? It's growing. The sides are growing, and it's a cube, so all the sides have the same length, and you could call it whatever you want, but I would probably call it X because I like X. You could call it S for sides. That'd be another excellent choice, or anything else you'd like. But that's certainly an unknown. That's a thing that's changing, right? So these unknowns here are going to be things that are changing. If they're fixed, then I don't really care about them. They're not going to affect the kind of rate in a meaningful way, and they're just going to be numbers. So I can plug those in later. But anything that's changing needs to be a variable. So the other thing that, of course, is changing, the sides are increasing at 2 centimeters per second. So the way we're going to write that using calculus is dx dt. So we're thinking of x as changing over time, right? As time goes on, x gets bigger and bigger and bigger. So it is a function of time. And so I can think of it having a derivative with respect to time. How fast is the function changing with respect to time? And I'm told that in this question it's 2. And I could keep track of the units here, although the units will work themselves out. Okay, so this is how we want to write that change. The other question for us is how fast is the volume increasing? So we don't know the volume exactly, right? That's kind of an unknown. It's something that changes. But we're not trying to find the volume. It doesn't say find the volume. It says how fast is the volume increasing? And that increasing is critical. That tells me that I'm looking at another rate. So the question is actually, let me see mine. That's what we want to find out. How fast is the volume changing? That's a derivative. And we're using this dv dt. You could write it as like v prime. That is meaning the same thing. But because we have different variables here, this is an implicit function. So when we write v prime, it's a little bit unclear what we're taking the derivative with respect to. Like, is it x? It's not actually x here. It's time that is the independent thing. These things are changing over time. So those are the derivatives, and that's a little bit why we use this dv dt option. Okay. So this is kind of setting the stage, defining these unknowns and the things that are changing. The critical step, once I have all this down, is I want to come up with an equation. And I'm going to say connecting the variables of interest. It's kind of my own little invention there of phrase, right? The variables of interest. In other words, what are the variables that I care about? There may be other variables like surface area, right? I don't care anything about surface area in this problem, so I don't want to include that in my equation. I need an equation that connects the things that I know to the things that I don't know. And I don't need to connect the rates. So this is the kind of magic of related rates. I need to connect the quantities or the functions. And geometric ones are typically the easiest here because there's just an obvious connection between v and x, right? Volume is x times x times x, or x cubed. Other really common equations are the Pythagorean theorem is really common. X squared plus y squared equals z squared, or whatever, a squared plus b squared equals c squared. So you'll see a lot of geometric ones. You'll see a lot of Pythagorean theorem ones. You'll see a couple trig ones, less common, but also out there. So look for those to kind of generate these connections. Okay, so this is what I want. This is an equation, but I'm thinking of this not as like a static equation, like x is a number and then v is a number. That's like a static equation. Think of x and v as like changing, right? These are both quantities that are growing over time. These are really functions of time. And so we can take their derivative implicitly with respect to t. So it's not x. We're not taking the derivative with respect to x here. Volume is related to x, but I'm not interested in how volume changes with respect to x. I'm interested in how volume really changes over time. Is really the underlying variable here. And I know sort of from my own thinking and from experience, it's a little hard to grasp what is happening exactly because, again, we're not super familiar with implicit functions. Okay. So I understand that. The good thing is, even if you're kind of shaky about how and why this is working, you can totally be successful in it, and then it'll start to make some sense as you do some of these, I hope. And even if it doesn't, you can still be successful. You just have to remember, when I take the derivative of a variable, I get d whatever dt. So the derivative of volume is dv dt, right? Because t is this underlying variable or this implicit function of t. And when I take the derivative of x cubed, x is another function of t. So I do the same kind of pattern. It's 3x squared. And then the chain rule, when I take the derivative of this function implicitly, is going to be dx dt. And some of you may, like the x there, may throw you off a little bit. So maybe that's a rationale for choosing like s or a and b, just so you don't think that you're taking the derivative like we have in the past with that as an x. What we've got here is that if v and x are connected this way, then this is also true, and this is connecting how fast v is changing to how fast x is changing. And this is actually the sort of magical equation for us, because this is connecting the things that we want to know to the things that we do know. Okay. So I want to know dv dt in this case. Sometimes dv dt or the part I want to know will be mixed up in other spots, right? But right here it's dv dt. That's what I want to know. That's equal to 3. Now it depends, like we said, the rate of change of the volume depends on how big x is, right? A little square, you're getting less volume than a big square than a giant square. So that's where we have to go back here. How fast is the volume increasing when the sides are 4 centimeters? So that's going to be 3 times 4 squared. And then I multiply by dx dt, which is constant at 2. So what is that? 3 times 16, 48 times 2, 96. 96. And if we're keeping track of the units here, this is dx dt is centimeters per second, and x is centimeters. So I get centimeters squared times centimeters per second. So that is going to be cubic centimeters per second. Okay, so I'm a mathematician. I'd be less picky about units than your physics teacher, but I do still care about them. So it's nice to verify that that's working, but it will work. The math behind it will make those units work out. If we do the same thing, kind of out of space here, but let me write that up here. dv dt equals 3x squared times dx dt. If we do that at 10 centimeters, notice, of course, it's giving me a much larger volume, which is what I would expect. So when the cube is 10 centimeters, the volume is changing at a faster rate, right? It's no longer 96 centimeters. It's now, what, 600? Yeah. A lot faster, which we would expect. Now, it's very hard to have a sense of, like, I have no clue over whether that number 96 or that number 600 are like reasonable answers. I can't visualize or calculate how fast the volume should be changing, but I can verify that it should be positive, right? We should be getting more volume as the sides increase. And as we talked about, the volume should be getting larger as x is getting larger too. So there's a little bit of a way we can check, but the actual numbers aren't something that we can kind of verify intuitively in some way. I have to trust the math. There are lots of other examples, even the ones I read in the beginning of class, right, or maybe seem a little different. I guess the snowball one is actually pretty similar. It's just a sphere instead of a cube, but the idea is similar. They all come down to the same kind of basic steps. I want a picture. I really need to make sure I define these unknowns. So to me, that's always a big step. Like if we're doing some of these problems and someone asks me for help and I look at it and they don't have like dv dt written down or dx dt, I'm like, well, you got to do that. We can't go anywhere until you do that, right? So make sure to do that step. It's important for helping us come up with the right equation and then just kind of helping us understand the result that we get. And it'll tell you, right? The unknowns sort of tell me what the equation needs to be. And then the other spot that people, it takes a little bit of practice to take this derivative implicitly when it's, in terms of t. But the pattern holds the same. Be careful if I have like x times y here for some reason, then I'd have to use the product rule if both x and y are functions of t. So you got to keep track of any variable there is a function of t, and you may have to use at least some of your derivative rules. So this was this is a pretty straightforward derivative for this one. Questions? It's such a weird feeling of sort of talking to myself, looking at myself on the screen, right?